Hi everyone, this is going to be the first lecture. Hopefully, you look through the week zero material, the videos that I posted from the content creator. Um, it's kind of giving you a review of Calc 1, just so you are prepared for what's coming up in Calc 2. First topic here that we are going to discuss is inverse function. Now, recall a convenient way of thinking about function is to think of it as doing something, which means that the inverse is can be thought of as undoing something, right? So, warning for the notation. Unfortunately, we use the notation f inverse with the negative one in the exponent, which in algebra means taking a reciprocal, but that is not the case of functions. It is not equal to 1 over f of x. So just be mindful of that. It's an algebra notation. In algebra, it's true, but for functions, that's not what it means. And also recall from the definition of function is for something to be a function and not a relation, you need that every input has exactly one output associated with it. You may have learned about it being called the vertical line test. Now, the reason behind that is because we are trying to use functions to model things that we use in our daily life. So we don't want things to be ambiguous. Now, if say you have a switch in your house, you turn on the switch and the light comes on. The next day you turn it on, it starts raining inside your house. You don't want that. So you want consistent output for every input. So that's part of the definition of a function. For example, this graph here is a function, whereas this circle here is not. Okay. As an exercise, I'll leave you to convince yourself why. Now, this means that the inverse function also has to be a function for it to be called an inverse function, right? So the requirement applies to the inverse as well. Now, in this box diagram, how things work is if you plug an input to the function, it gives you an output. If you take that output and plug it into the inverse function, it gives you back the input. Remember, the input and the output switch places for an inverse function, right? So the inverse function is undoing it. Now, based on our requirement for what a function should do, what this means is that every output must have a unique input associated with it, right? Because in this case, the output is the input and the input is the output. So we can say that the condition for existence of an inverse function is that the function that you're trying to take an inverse of has to be one to one. Another way of calling it is an exclusive function. There's an exclusive relationship between the input and the output. Um, and yet another way, algebraically, of saying that is that f of x1 is not equal to f of x2 whenever x1 is not equal to x2. Okay. Next section, we're going to look more into the so-called one-one functions or exclusive functions. This property that we just described is called being one-one. Here's a small concept check problem for you. This condition can be checked whether a function is one-one by something called a horizontal line test. How and why does that work? You can think about it. In the meantime, let's look at an example. Is f of x. Let's look at an example. Given a function x squared, we're trying to figure out if it is 1, 1. One way to do that is to draw the graph. You know it looks like an upward facing parabola with the vertex at the origin. Horizontal line test, well, it has two intersections, which means for the same, or you can have two inputs with the same output. Hence, it is not 1, 1. Another way of doing it is pick two values of x1, x2, which are not equal, so 2 and negative 2, but their squares both equal 4. So what you have is that f of x1 equals f of x2, but x1 does not equal x2, so it is not 1, 1. So these are two ways of checking if a function is 1, 1. Next example, let's look at x cubed. Again, two ways of doing it. Graphically, it's pretty obvious that it is 1, 1. Um, Here's another concept check problem that you can pause the video and think about it. What can you say in general about the function f of x equals 1 over x to the n for different values of n? And let's only consider, for simplicity, integer values. So n equals 1, 2, 3, 4, so on. This is a bonus question number one for this lecture. The statement is that 1, 1 functions are monotonically increasing or decreasing. The definition of monotonically increasing or decreasing, what you've seen in Calc 1, is either in terms of the derivative being positive or negative, or you think of them as functions which are never constant at any two given points. They always are either increasing always or always decreasing. So the bonus question is this statement true or false? Why or why not? Um, I will be creating a bonus assignment tab on Google Classwork and Classroom. And what you can do is, if you want to respond to this problem, you can add your responses over there and they will be graded. Okay. So far what we have is inverse functions, what they are, um, what are the conditions necessary for creation or existence of an inverse function, and that condition being the property of being 1, 1. And then we learned how to check if a function is 1, 1 algebraically or geometrically. Additionally, if you consider the bonus question, we've also already established a calculus method of finding if a function is 1, 1, which is just by seeing if it is monotonically increasing or decreasing. All right, I'm going to end this video here.